Hi everyone, this is Ranjit, and in this video we are going to look at an algorithm to compute the closest point on a mesh from a given query point. Now, this is a standard feature in Grasshopper and Rhino, but we are going to implement this ourselves and in the process learn how it works. So I'm trying something new in this video. Instead of explaining the concepts first and then giving the walkthrough of the code, I'm going to try and do both at the same time. So yeah, let's see how this works. To compute the closest point on a mesh, the first thing we do is to query the mesh vertex R tree for the nearest vertex index. We are going to start with this nearest vertex as our first guess as to where the closest point is, and we are going to store the squared distance to this point in a variable named best distance squared. Now, this is probably not the actual closest point, but this is just a starting point. We are going to refine our guess as we go along. Next, we check if the nearest vertex is within the search distance. And if it isn't, we can bail out early. We don't need to compute the closest point at all. But if it is within the search distance, we create a box centered around the query point with the edge length equal to 2 times the distance to the nearest vertex. Because our best guess so far for the closest point is this vertex, if there's a better guess, it has to be inside this box. So we query the mesh face R tree for all the faces that intersect this box. The actual closest point must be on one of these faces, and querying the R tree like this for a subset of faces is actually a lot faster than looping over all the faces of the mesh. We then loop over these faces that are returned by the query, and for each face we compute the closest point on that face from the query point. And we use that to update our best guess. To understand it clearly, let's focus on finding the closest point on a single triangle. Let's jump into the definition of this function. To compute the closest point on this face, we get the first vertex of the face, the normal of the face, and store them in local variables. We get a vector that joins the query point to the first vertex of the face, and compute the component of that vector parallel to the normal of the face. What that gives us is a projection vector that projects the query point onto the plane of the triangle. Now, if the length of this projection vector is longer than the best guess that we have so far, that means the closest point does not lie on this triangle. It means the plane of the triangle is too far away from the query point to matter, so we can bail out early. But if the distance to the plane is not greater than the best guess so far, we project the query point onto the plane of the triangle and loop over the edges of the triangle. For each edge, the projected point might be on either the outer side of the edge or the inner side of the edge. So to find out which side of the edge the projected point is on, we compute the normal of the triangle formed by the edge and the projected point, and calculate the dot product of that normal with the face normal. So if the point is on the inner side of the edge, the two vectors, the two normals, would point the same way. But if the point is on the outer side of the edge, the two normals will point in opposite directions, so the dot product will end up being negative. So we store the result of this test in a Boolean variable named outside. And if the value of that Boolean variable is true, we update the counter we created before to keep track of how many edges we are having to process. That is, how many edges have the projected point on their outer side. We then compute the closest point between the edge of the triangle and the projected point by pulling the point onto the edge and clamping it to be between the two vertices. If this closest point is closer than the best guess we have so far, we update our best guess. And after processing each edge like this, if we realize that our outside edge counter is greater than 1, we can bail out early and we don't have to process all the edges. This is because a point in the plane of a triangle can only be on the outer side of at most 2 edges. It cannot be on the outer side of all 3 edges. And finally, after we are done looping over the edges, if it turns out that the projected point was not on the outer side of any of the edges, that is, our counter is still set to 0, That means the projected point is inside the triangle, which means the closest point is the projected point itself. You might have noticed here that we are not comparing the new values with the best guess before updating it. That is because we already did that comparison and made sure that the distance to the plane is not greater than the best guess, so we don't have to do that comparison again. So when we are done running all the logic inside this function, if the closest point on this triangle is closer than the previous best guess, we will have updated our best guess. And back in our closest point function, we loop over all the candidate faces and refine our closest point estimation along the way until we end up with the actual closest point, which we return from this function. The closest point function is called from inside the pinvoke function. We store the closest point in a local variable and then copy its coordinates into this buffer. Let's take a look at our C# function. In there, we first convert the Rhino mesh into an unmanaged mesh. We create an array with the coordinates of the query point. We also create an empty array to which our C++ code is going to write the coordinates of the closest point. After calling our pinvoke function, we delete the unmanaged mesh and finally return the closest point. Now let's test our algorithm. I have once again the bunny mesh here, and I created several random points and computed the closest point from each of the random points. And it looks alright. And I did the same using the built-in grasshopper component and computed the distance between the two results. As you can see, the error is quite small, and yeah, that's acceptable. Now, there are a lot of things you can do to improve the performance of this algorithm, but the point of this tutorial is to demonstrate the basic logic for computing the closest point on a mesh. So with that, I'll conclude this video, and thanks for watching. I'll see you in the next one.